everyone. My name is Zhichao Lu. I'm here today on behalf of my co-authors to share with you our recent work of neural architecture transfer. Recent years has witnessed growing interest in neural architecture search, or NAS in abbreviation. In the meantime, real-world deployment requires these NAS algorithms to accommodate diversely different scenarios, including data, hardware, and resource-related requirements or objectives. And oftentimes, these different requirements or objectives needs to be simultaneously satisfied or improved. To achieve this, we need a NAS method that is efficient and scalable in finding the best set of trade-off network models for these diverse deployment scenarios. Based on our survey on the existing NAS method, we observed that most of the methods have only been evaluated on Cipher10 and ImageNet, where both of these datasets has sufficient training data and well-studied training hyperparameters. Also, we observed that most of the methods are single or bi-objective driven, for example, maximizing accuracy and minimizing latency. We rarely find any method that handles 3 or more objectives. In this work, we demonstrate the practical utilities of our method by searching on 11 datasets and 12 objectives. As previously said, existing NAS methods were mostly applied on Cipher10 and ImageNet, where the search finds an architecture topology and corresponding weights. When it comes to other datasets like Oxford Flowers, they typically follow the standard transfer learning routine, where the architecture learned on standard datasets are directly applied without changes to new dataset with weights fine-tuned. Despite the efficiency, this approach of fixing architecture will lead to inefficiency in case of simple tasks and a deficiency in performance in complicated tasks. Our method follows a different approach. First, we adopt the supernet route, where all searchable architectures become subnetworks and their weights are directly inherited from the supernet. And when it comes to other datasets, we apply transfer learning at a supernet level and carry on the search to find new subnetworks that are suitable to the new dataset. This approach in principle leverages the efficiency provided from both the supernet and transfer learning such that searching on every dataset becomes feasible and the task-specific architectures can be now found efficiently. To be more specific, let's consider the existing supernet approach, which works as follows. It starts with a warming up period by training the supernet at its full scale. Then it undergoes a progressive training process, where in each iteration, a subpart from the supernet is randomly selected and fine-tuned. The trained supernet is then supplied to the subsequent architecture search algorithm for finding the suitable subnetworks. The key to the success of this decoupled approach is that all subparts of the supernet need to be trained equally or simultaneously, as which subparts are optimal for the task at hand are usually unknown before search. And we argue that this approach is practically not scalable to the size of the search space, and more importantly, it is also unnecessary. To solve this chicken and egg problem, we use the architecture search algorithm to guide the training of the supernet, and in our case, we use a many-objective evolutionary search method. Now, during each iteration of the progressive training, we apply EA to search for the promising subnetworks under the current supernet, and only fine-tune the subparts that are corresponding to these promising subnets. The architecture from the EA search at the end of the training iteration become the output models. As you can probably imagine, repeating this process to train a supernet for every dataset is computationally intensive. Instead, we transfer the weights from the supernet that was trained on ImageNet and fine-tune on the new dataset during progressive training. To further improve the search efficiency, we learn a surrogate model to predict the accuracy of subnetworks. A typical process of architecture evaluation during search is shown here. The SGD training is skipped with the presence of supernet, but inferencing on validation data is still required for measuring the performance. An accuracy predictor aims to directly relate architecture encodings to their performance from samples, which further reduces the evaluation time as now no data processing is needed. Our accuracy predictor is an ensemble model of 500 radial basis functions. where each RBF is constructed based on a random subset features from architecture encodings. We validate the effectiveness of our accuracy predictor on 11 datasets, and empirically, we find our predictor model outperforms other models from the literature, especially under limited number of training samples. We first show the performance of our method on ImageNet under a bio-objective setup to maximize accuracy and minimize flops. In general, our method outperforms other manually designed and NAS-generated models, including NATNet and EfficientNet. We then zoom into mobile setting region, where again, our method outperforms a wide range of existing NAS methods. In particular, we achieve 80.5 top 1 accuracy, a new state-of-the-art on ImageNet under mobile setting. We then show the scalability of our method to different datasets. We first compare with EfficientNet on 3 datasets with different types of data, different number of classes, training size, and image resolutions. In general, our method, which directly search on each dataset, significantly outperforms EfficientNet, which transfer fixed architectures from ImageNet. A similar trend is observed when we extend a comparison to many other models and datasets. The search couple parameters are chosen such that the search finishes in 1 day on an 8 GPU server for each dataset. Towards understanding of the observed improvement in performance, we visualize the Pareto optimum architectures obtained by our method, where we clearly see different datasets require different architectural settings, including input resolution, width, kernel sizes, and etc., to optimally trade off accuracy and efficiency. Next, we show the scalability of our method to a large number of objectives, where we simultaneously maximize the top 1 accuracy on 11 datasets and minimize the flops. We show the Pareto optimum architectures obtained in this parallel coordinate plot, where each vertical bar represents an objective, and each line joining all vertical bars represents an architecture. First, the crisscross of these lines indicates trade-off among these 11 datasets exist, otherwise these lines will be parallel to each other. We then pick the architecture with the highest trade-off and compare it with 4 existing models, where our model outperforms the compared models on all datasets as shown to the right. To summarize, in this work, we introduce neural architecture transfer for efficient search for diverse deployment scenarios. It comprises of 4 main components, including a many objective EA, a supernet with transfer learning, and an accuracy predictor. The proposed method improves the current approaches in a number of ways. In particular, a new state-of-the-art on the ImageNet under mobile setting is achieved, and the scalability of the proposed method is extensively evaluated on many datasets and objectives. The pre-trained models on all datasets are available on GitHub. Thank you.